All right, here's one from chapter 7, number 48. So there's the problem. You should read the problem for a second, and then we'll see what we can do. This one is a little tricky. You got to read it carefully. So what you have is you have a rope that is extended between two supports, and this is 10 meters across. But each of these has a 10-degree angle here. Okay? So that essentially the guy standing here, so it's supported over here, it's supported over there, is standing on this rope that's sagging in the middle because he's standing on the rope. And when he's standing on the rope, he goes and he jumps to force himself to jump up off of the rope as he's standing there. Well, while he's doing that, he's applying a force. To accelerate up, he has to apply a downward force to make that occur. Right? So, remember, equal and opposite. So that from here, we have to figure out what the tension is the rope in as he jumps. So it sounds complicated, but it's not bad because we just do it the same way we always do all our problems. We're going to do a free body diagram on the guy. So the guy has a mass, mg. Okay? And we have tension going this way. We have a tension going this way. Now because he's standing right in the middle of the rope and both of those angles are exactly the same, those tensions are exactly the same. It's equal. Okay? So I'm just going to call it T. Now if he wasn't in the middle or the angles were different, then you would have to have a T1 and T2, they would be different. But that's not the case here. Okay? And then he applies a force to accelerate himself upward. Which way is he applying that force? Well, he's actually applying that force in a downward direction because he wants to accelerate up. So you have to push off the ground to accelerate up. He's pushing the force here. He feels the force going upward, right? So a free body diagram would make him accelerate upward, but the rope right here is going to feel a downward force. Okay? That's the only forces acting on it right there. Okay? And this is the rope. This is not the guy. I might have said that wrong before. But this is the free body diagram of that point in the rope, what forces are acting on that. All right, so this is 10 degrees. This is 10 degrees. So we have T cosine 10 degrees that way, T cosine 10 degrees that way. And then we have two forces going up, T sine of 10 degrees this way, and T sine of 10 degrees this way. So I just split the tension forces into their components. Okay. Notice that in the x direction, if we did f and x, we just have t cosine 10 equals t cosine 10, which is true. It doesn't tell us anything though. We can't solve that. We don't know what that means. So we have to do it in the y direction. The y direction is what matters here. So we're going to do f net y is equal to t sine of 10 degrees plus t sine of 10 degrees minus mg minus f. That's his applied force. Yeah. We want to solve this for t. Okay? Now right when he's jumping, he's accelerating, but the rope is not. So this is just equal to 0 because the rope is not doing the acceleration. So what I'm going to do is I'm going to combine these. This just becomes equal to 2t sine of 10 degrees minus mg minus f. All right, I'm going to move these over to this side. So this is going to be mg plus f is equal to 2t sine of 10 degrees. And then we want to solve this for t, so I'm just going to divide by all that. I'm going to get t is equal to mg plus f over 2 sine of 10 degrees. But the question is, what's f? Well, it says in the problem that he accelerated at 8 meters per second squared, and we know his mass. So for him to accelerate upward, he had to have a net force on him. That net force has to be the same as F force. So the force that he's feeling accelerate him up is the same force that is here because it's contact force, Newton's third law. So the F is just going to be equal to his mass times its acceleration. So this is going to be equal to mg plus ma over 2 sine of 10 degrees. We can plug in the numbers, and this is 70 times 9.8 plus 70 times his acceleration, which was 8, all divided by 2 times the sine of 10. And if you do that, you get a value of 3,590 newtons. We only had 2 sig figs, so it's actually 3,600 newtons. All right, that's a lot of tension. But that's how you have to do it if you're doing a tightrope. You have to have it very strong on the ends. So there's a lot of tension in the rope. Does that make sense? As you can see, it's not a hard problem once you get it set up. The hardest problem is figuring out how to set it up. All right.